Okay, in this video I'm going to talk about the special case of Miquel's theorem when the points are collinear. So recall that there is a Miquel's theorem, which is also sometimes called pivot theorem. Let's write it here. Pivot theorem. So and the theorem is like it says that if we have a triangle and we take a point on each side, like arbitrarily, something like this, then or on the sides or on the extensions of the sides, like it doesn't matter, and we consider the circumcircles of these three triangles formed by the vertices and by the points. Then these three circles intersect at a single point, which is also sometimes called the Miquel's point. So this theorem I proved it in one of the previous videos. So now there is a special case when these 3 points on the sides are collinear. So let's say that we don't just take 3 arbitrary points, but we take 3 points that are collinear. So it means that we take a line, take the intersection points of this line with the sides of the triangle, so these 3 points, and we similarly construct the circumcircles of the triangles. So we take this circumcircle, we take this circumcircle, and we take this circumcircle. So they still intersect at a single point, but now the theorem is that, so if we have the special case that the 3 points are collinear, then this Miquel's point, the point of the intersection of these 3 circles, also belongs on the circumcircle of the original triangle. So the circumcircle of the original triangle also passes through this point, and the converse statement is also true. So if the Miquel's point lies on the circumcircle of the original triangle, then the 3 points on the sides are collinear. So let's write this as a theorem. So let's denote the original triangle is ABC. The points that we take, let's denote them by D, E, F, and let's denote the circumcircle of the original triangle as omega. So now and the Miquel's point denoted by M. So now the theorem says that M belongs to the circumcircle of the original triangle omega if and only if D, E, F are collinear. So okay, so let's prove it. So we will proof. We will start in this direction. So we assume that So we assume that DEF are collinear, and we will prove that M belongs on the circumcircle. So in this case, so I will remove this circumcircle. We don't yet know, well, not the whole circumcircle, but I will remove the part that passes through M, so we don't know that yet. We need to prove that. And the fact that these three circles intersect at a single point, this is already proved, but I like quickly remind how to prove it. So basically we have, because like we will need basically these angles anyway, so because yeah, so actually let's draw another picture. It would be more convenient not to draw the circles at all at first. So we have a triangle, we have a line, so A, B, C, D, E, F, and we consider first the intersection of two circles. Right, so let's say this circle and this circle. We consider this point M. So yeah, so we connect like this. So because the quadrilateral, so this is point P. So because of the first circle, because the quadrilateral FBMD is inscribed, so these two angles are equal to each other. They subtend the same arc BM in this circle. And because of the second circle, the quadrilateral DMEC is inscribed, we have the external angle, so BDM. So this angle is an external angle in this quadrilateral, and it's equal to the opposite internal angle. So these two angles are equal. So BDM is equal to MEC, right? And now we have the chain of two qualities, right? So we have BFM, this angle BFM is equal to MEC, and these two angles in the quadrilateral, so in this quadrilateral that I highlight with blue, so these two angles are internal at one vertex E and the external at the opposite vertex F. So therefore, because these two angles are equal, therefore this quadrilateral is inscribed, and therefore the point M lies on the circumcircle of the triangle AFE. So this proves basically the Miquel's theorem. So now if we have the additional condition that DEF are collinear, then basically what we have is that so these two angles are equal to each other, right? FDB is equal to CDE. Then because of the then each of them is equal to another inscribed angle in each of the circles. So if you draw it like this, so FDB is equal to this angle FMB, right? Because they both subtend the arc FB. The arc FB, so FDB is equal to FMB. And in the other circle we have CDE is equal to CME. Okay, so now because of this this equality of this angle, so we basically can add the same angle to both of them, so the angle FMC. So from this we conclude that this angle FME, so FME, this angle, is equal to the angle BMC. So let's write this. So the angle FME is equal to the sum of two angles, so is equal to the angle FMC plus the angle CME, right? So now the angle CME, we just proved that it is equal to the angle FMB. So the first we rewrite as it is, FMC plus, and CME we replace with FMB, and now we look like FMC plus FMB, FMC plus FMB, this is exactly the angle BMC. Right. So basically, like these two angles, like CME and FMB, these two equal angles, we add to both of them the same angle FMC, and we obtain the equality of these two angles FME and BMC. So okay, so let's write this separately. So the angle FME is equal to angle BMC. So now basically we observe that one of them, so in the quadrilateral AFME, so the quadrilateral AFME, so in this is an inscribed quadrilateral. This is basically like that is highlighted in blue on the picture, AFME. So in this quadrilateral FME, this angle is one of the angles at the vertex M, right? So because it's an inscribed quadrilateral, so the opposite angle must be 180 degrees minus FME. So the angle A must be 100. Oh, let's write the angle A plus the angle FME is equal to 180 degrees, right? So this is the one of the criterion of the inscribed quadrilateral. So angle A plus the angle FME must be 180 degrees. So now because FME is equal to BMC, we can replace FME with BMC. So this implies that the angle A plus the angle BMC is equal to 180 degrees. And this basically is what we need. So A plus BMC, so the angle A plus the angle BMC. So now we consider this green quadrilateral, and so the angle A is this one, and the BMC is this one. So they're the opposite angles in this quadrilateral. So this means that since the sum of these two angles are equal to 180 degrees, it implies immediately that this quadrilateral is inscribed or cyclic. So ABMC is cyclic. And this means that M belongs on the circumcircle of ABC, which is omega. So this is exactly what we need to prove. So this concludes the proof for this part. And the converse statement, so the converse statement, we now assume that M lies on the circumcircle, and we need to prove that the points D, E, F are collinear. So basically we do the same arguments, but from the end to the beginning. Like basically, like all the arguments they were invertible kind of. So like they were equivalent. So like let's do it actually. So now we have this triangle, these 3 points. So let's draw them deliberately not on the same line. So something like this. And we know that the circumcircles, so when we draw the intersection, so this is the Miquel point. So A, B, C, D, E, F. And now we know that the Miquel point belongs on the circumcircle. So it lies on this circumcircle. And we need to prove now that DEF lie on the same circle. So because so from the general Miquel theorem, we know that the angles. So again, let's reconstruct it. We know that which angles we consider it. Oh, but it doesn't matter now. So okay, so yeah, so we consider now this. And this. So because ABMC, so ABMC now is cyclic because M lies on the circumcircle. From this we conclude that the angle A plus the angle BMC is equal to 180 degrees. From this we conclude that, yeah, also we know that the angle, so AFME is cyclic. From this we know that the angle A plus the angle FME is equal to 180 degrees. So from these two equalities we conclude that BMC is equal to FME, right? Because everything else in the equalities is the same, like we can subtract one from the other. So from this we conclude that the angle BMC is equal to the angle FME. FME, and now so BMC is this angle and FME is this angle. So now they have the common angle FMC. So if we subtract FMC from both of them, so so we write that the angle FMB, this angle, is equal to the angle BMC minus the angle FMC. BMC now we replace with FME. So this is equal to FME minus the angle FMC. And FME, so FME, this large angle, minus FMC, minus FMC, this is exactly the angle CME. So we conclude that FMB is equal to CME. So this angle is equal to this angle. Now we construct the equalities like this angle is equal to this as two inscribed angles in the same circle subtending in the same arc, FB, and this angle CME is equal to CDE as inscribed in the same circle subtending in the same arc CE, right? So we write that, so the angle FDB is equal to the angle FMB, which is equal to, just as we proved, to the angle CME, which is equal to the angle CDE, right? CDE, because they subtend the same arc CE in this circle. So in total we have FDB is equal to CDE. So FDB is equal to CDE, right? So like if I draw it on a separate picture, so we have this side BC of the triangle, we have these points, so here somewhere E, D, F, and we just proved that this angle is equal to this angle. Well, this, so FDB is equal to CDE. This immediately proves that FD and E lie on the same line, because if we extend this way, like this angle would be equal to this, and now we have two angles, so two angles with the same side, so this angle is equal to this angle. This can only be if this is the same line. So this immediately implies that D, E, F are collinear, and this concludes the proof.